This is a presentation by Ariana Chae, Sebastian Dziallas, and Mandy Korpusik. In this video, we are going to talk about metadata integrity. Maintaining and assuring the accuracy and consistency of metadata in file systems is important, especially in the case of a sudden and unexpected system crash. When a single logical transformation of the metadata from one state to another is implemented by writing several individual blocks to persistent storage, metadata integrity is threatened because a shutdown may stop the writing process and data can be lost or saved incorrectly. For example, if a new data block is added to a file, the metadata index node, or inode, will point to the new data block, and the block bitmap will show that the new block is no longer free. However, if the system crashes when only one of these two updates has happened, the metadata will be inconsistent. There are three kinds of violations. First, there is irreparable corruption, where two files are given equal rights to a single data block. In this example, the file's metadata points to the block, but the bitmap is not updated to show that the block is no longer free. Thus, another file could try to use the same block, even though it is already in use. There is also noncritical reparable corruption, where a data block is lost but can be repaired at any time. In this example, the file is not actually using the new block because the information was not saved, but the block appears to be in use, resulting in a lost block. Finally, there is critical reparable corruption, where a data block is marked as free, even though it is in use. This must be corrected before the system returns to normal operation. If it is not corrected, it will result in irreparable corruption. There are four types of solutions to this problem. The solutions are journaling, shadow paging, synchronous writes, and soft updates. Synchronous writes and soft updates entail carefully controlling the order of updates when making logical changes to the metadata state, and running a consistency repair program after each system crash. However, this takes a long time, making these options unpopular. We will now discuss the more popular solutions, journaling and shadow paging, and highlight an implementation of shadow paging in the Btrfs file system for Linux. In both journaling and shadow paging, a single block is written to persistent storage when metadata is changed. Journaling is the most widely used strategy for maintaining metadata integrity. A journaling file system keeps track of changes that will be made in a journal before committing them to the main file system. The time it takes is proportional to the amount of activity logged since the last checkpoint, rather than to the file system size, which makes it faster than synchronous writes and soft updates. In journaling, the current metadata structure is modified, so the single block is the commit record in the write-ahead log. Only the writing of the commit block creates a real state change, which is highlighted in the green box of this diagram. After a crash, the system is rolled back to where the commit record has last been written. Shadow paging is a type of copy on write, or COW. In shadow paging, a new metadata structure is created, instead of changing existing ones each time a page is to be modified. A single block is written to point to the current metadata structure. The new metadata structure, called the shadow page, does not overwrite the original page, but instead is recorded at another place on the disk. Thus, at any time a data item has a shadow page, both copies are at two different places on the disk. This is shown in step 1 of this diagram. When the page is ready to be written to persistent storage, all pages that referred to the original are updated to refer to the new replacement page instead. This process is isolated from concurrent processes and cannot be interrupted, ensuring that it will be successful. This can be seen in step 2 of this diagram. A benefit of shadow paging is that it supports snapshots, which keep track of prior versions of the file system's contents. Increasing demand for snapshots may lead to increased use of shadow paging. One of the recent examples where shadow paging is actively used is the file system Btrfs for Linux. With Btrfs, data and metadata are protected with copy on write logging. Once the transaction that allocated the space on disk has committed, any new writes to that logical address in the file or B tree will go to a newly allocated block, and block pointers in the B trees and superblocks will be updated to reflect the new location. In conclusion, by writing a single block to persistent storage when transforming metadata through journaling or shadow paging, we can efficiently and reliably maintain metadata integrity.